There is a machine on every major construction site that does something almost no other machine on Earth can do. It builds the building, and while it is doing that, it also builds itself. It gets taller as the structure beneath it grows. And when the building is finished, it somehow comes back down. The tower crane is one of the most elegant pieces of engineering in the built environment, and almost nobody stops to think about how it actually works. Most people see a tower crane and just register it as a tall thing with a horizontal arm that lifts stuff. That is accurate, but it misses the engineering. A tower crane is a fixed-height rotating crane anchored to the ground, with a horizontal jib that carries the hook and a shorter counter jib on the opposite side that carries concrete counterweights. The whole assembly sits on a mast, which is a vertical steel tower made of interlocking lattice sections. The crane operator sits in a cab at the very top, just below where the jib connects to the mast. Every movement is controlled from that cab, sometimes from a height of 200 meters or more. The key characteristic that separates a tower crane from a mobile crane is that it does not move. It is bolted to a concrete foundation pad poured specifically for it before any other construction starts. That foundation pad, depending on the crane size, might weigh as much as 400 tons. Some large cranes are also tied back to the building structure itself at regular intervals as the building grows, which allows them to reach even greater heights. But the foundation is always the starting point, because everything else sits on it. Before a tower crane can lift anything, it has to be built. And building a tower crane requires a smaller mobile crane. This feels like a circular problem until you understand the sequence. The mobile crane arrives on site first, assembles near the foundation pad, and lifts the first sections of the tower mast into position. These mast sections are typically 2 to 3 meters square in cross-section and 3 to 6 meters tall. Each one is lifted and bolted to the one below using high-strength structural bolts. Once enough mast sections are stacked to give the crane its initial working height, the slewing unit is installed at the top. The slewing unit is the ring gear mechanism that allows the entire upper section of the crane, the jib, the counter jib, and the cab, to rotate a full 360 degrees. A hydraulic motor drives the rotation, and on a well-maintained crane you can barely hear it move. Then the jib itself is lifted into place. The jib is the long horizontal arm, typically between 40 and 80 meters in length, along which the trolley travels to position loads. The counter jib goes on the opposite side and the concrete counterweights are stacked at its far end. Now the crane is standing, but it is at a fixed height and the building it is going to build will eventually be much taller. So how does it grow? One detail that surprises most people is how the foundation is anchored. It is not just a matter of setting the base plate on concrete. The crane manufacturer specifies an anchor bolt cage, a large square array of high-strength steel bolts that are cast into the concrete pad before the pour. The concrete is then cured around them for at minimum a week, often longer on large cranes, before any crane weight can be applied. When the base section is lowered onto the anchor bolts and the nuts are torqued down, the connection has to resist not just the crane weight but the overturning moment created when the jib is carrying a full load at maximum radius. On a large crane, this overturning moment can exceed 2,000 ton-meters. The foundation and anchor bolt design is a structural engineering problem in its own right, separate from the crane manufacturer, and often engineered by a local firm retained by the contractor. This is the part that genuinely surprises people when they first understand it. A tower crane raises itself using a hydraulic climbing frame, a mechanism built directly into the mast. Here is how it works. Inside the mast, or surrounding it depending on the design, there is a steel collar with powerful hydraulic rams. When it is time to add height, the climbing frame is activated. First, the entire upper section of the crane, the jib, counter jib, cab, and slewing unit, is lifted slightly off the top of the mast by the hydraulic rams. This creates a gap of roughly 1 mast section height between the top of the existing mast and the underside of the climbing frame collar. A new mast section is then swung into position using the crane itself, because the crane is still operational during climbing. The new section slides into the gap and is bolted in place. The hydraulic rams then release, and the upper assembly settles onto the new section. The crane is now 1 mast section taller. This process takes a few hours and can be repeated as many times as needed. Some large skyscraper projects repeat it dozens of times. The crane essentially leapfrogs upward, always staying ahead of the building floor by floor. What makes this remarkable is that the climbing operation uses the crane to lift its own components. The machine participates in its own vertical extension. A tower crane is fundamentally a lever balancing act. The jib sticks out on one side, carrying whatever is being lifted. The counter jib sticks out the other side, carrying the counterweights. For the crane to remain stable, these two moments, the technical term for force times distance, have to roughly balance. The problem is that the load on the hook changes constantly. You might lift a 40-ton steel beam 1 hour and a 1-ton bundle of rebar the next. The crane handles this through the position of the trolley on the jib. When a heavy load is close to the mast, the moment arm is short. When a lighter load is at the tip of the jib, the moment arm is long. The crane operator has load charts that specify exactly how much weight can be lifted at each position along the jib. These are not guidelines. They are hard limits enforced by electronic load monitoring systems that will cut power to the hoist if the safe working load is exceeded. Modern tower cranes also have anti-collision systems that track other cranes on the same site, because large projects often have multiple cranes whose jibs can overlap. When two jibs are in the same airspace, one must always remain higher than the other, and operators coordinate through radio. The counterweights themselves, which are stacked concrete blocks, typically weigh between 20 and 30 tons in total on a mid-size crane. They are installed during erection and removed during dismantling. You cannot add more load capacity by adding more counterweight. The entire system is engineered as a match set. The crane operator climbs to work every day, and on a tall building that means climbing a ladder inside the mast for 15 or 20 minutes before the shift starts. Some larger cranes have a small lift inside the mast, but many do not. The cab itself is compact, roughly 2 meters by 1.5 meters, with a seat, a bank of controls, and windows on all sides. Operators sit facing the jib and work with 2 joysticks that control hoisting, slewing, and trolley travel simultaneously. Below them, the site can look like a model, and on hazy days the top of the mast can be in cloud while the ground is in sunshine. Communication with the slinger on the ground, the person who attaches loads to the hook, is typically by radio, sometimes with hand signals when close. The challenge of the job is spatial. The operator cannot always see the hook, especially when it is directly below the cab. Banks of cameras are increasingly common on modern cranes, but many operators still rely on their sense of feel and communication with a banksman on the ground who guides them in. Wind is the other constant factor. Tower cranes have wind speed limits, typically around 14 meters per second for normal operation, and they must be locked off in high winds. When the crane is not working, the jib is released to weather vane, meaning it rotates freely to face into the wind rather than acting as a sail. This is why cranes swing slowly on windy nights even when no one is in the cab. There is also a significant psychological element to crane operating that does not appear in the training manuals. On days with strong winds, the entire mast sways. On a 200-meter crane, the top can move laterally by half a meter or more, a motion you can feel in the cab. Some operators find this disturbing. Others say they stop noticing it after a few months. Vertigo is disqualifying during the pre-employment medical, and most crane operators simply do not have it. But the isolation of the cab, the physical separation from every other worker on site, combined with the responsibility of moving loads that could kill if dropped, creates a job with a particular kind of pressure. Experienced operators are among the highest-paid tradespeople on any large construction site, and the shortage of licensed crane operators in many countries means that demand for their skills consistently outstrips supply. When the building is complete, the crane has a problem. It is very high up, and the mobile crane that helped build it is not tall enough to take it down from the outside. The solution is essentially the reverse of the climbing process, and once again the crane participates in its own dismantling. The hydraulic climbing frame is used to remove mast sections one by one, lowering the upper assembly down until the crane is at its minimum working height. At that point, a smaller mobile crane can handle the final dismantling of the jib, counterjib, and remaining mast sections. On some very tall buildings where the crane is tied to the structure, the process is more complex. The upper tiebacks must be removed floor by floor as the crane descends. Some projects solve this differently by building the crane into the building itself during construction and then cutting it out afterwards, patching the floor penetrations. There is also a technique called internal climbing, where the crane sits inside the building structure rather than on an external mast and climbs upward through sequential floor openings. This is used when the footprint is tight or when the building design makes external masting impractical. Every tower crane dismantling is a custom engineering operation with its own sequence and its own risks. The final removal of the base section from the foundation pad is done by mobile crane, and what is left is just a bolt pattern in a concrete pad, soon to be buried under finished landscaping. One frequently overlooked aspect of tower crane dismantling is the legal and regulatory dimension. In most jurisdictions, erecting and dismantling a tower crane requires a licensed crane supervisor and a separate lift plan. A document that details every stage of the dismantle sequence, specifies the mobile crane to be used, identifies exclusion zones below the work, and is signed off by a structural engineer. This paperwork exists because dismantling accidents are historically the most dangerous moment in a tower crane life cycle. During erection and operation, the loads are generally well understood, and the machine is in its designed configuration. During dismantling, sections are being separated that have been torqued together for months or years. The sequence must be precise to avoid imbalance, and there is always the risk of components binding or bolts that have corroded in place. Tower cranes are not just machines. They are an expression of a design principle that recurs throughout engineering, a system that uses its own capacity to extend itself. The same logic appears in space station construction, in deep-sea pipeline laying, in the extension of suspension bridge cables. The constraint is always the same. You are working at the frontier of what exists, and the only resources you have are the ones already in place. The tower crane solved this on construction sites in the middle of the 20th century, and the solution has not changed dramatically since. The hydraulic climbing frame that was patented in the 1950s is still the mechanism used today. What has changed is scale. The tallest tower cranes now operating reach over 250 meters. The largest have a maximum load capacity of over 80 tons at the hook. Projects like the Burj Khalifa in Dubai required cranes that had never been built before, purpose-designed for a single project. Some of these record cranes cost more than $50 million each. But the principle is the same as the relatively modest crane on a medium-rise residential project in any city. It builds the building. And while it does that, it builds itself. The next time you walk past a construction site and look up, the tower crane is not just a machine. It is a problem that solved itself. The engineers who designed it understood that to build something taller than any existing machine could reach, you had to build a machine that could reach beyond itself. That idea of a system that extends its own capacity while doing its primary job is one of the most useful in all of engineering. And it is playing out every day on sites around the world, one mast section at a time.